Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called redundant connection. In this problem, a tree is an undirected graph that is connected and has no cycles. Alright, so we're starting off with a definition, pretty cool. You're given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array edges of length n, where edges of I is equal to a of I, b of I. Indicates that there is an edge between nodes a of I and b of I in the graph. Alright, a lot of information in this paragraph right here. What we know is that our graph was initially a tree, and they have inserted an extra edge that no longer makes it a tree. Now this extra edge that was added connects two different vertices. It does not make a loop in the graph. Where a loop in a graph is there's an edge from 2 and it goes to 2. They're also defining what our edges array represents, which gives us the information that we need to represent this graph. Now one thing that I added myself was that this extra edge no longer made it a tree. That's actually given here in the final paragraph. But everything else was made obvious just from reading this. So they want us to return an edge that can be removed so the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. So I'll explain what exactly they mean by this in my drawing. I can also explain it right here just by using my mouse, if you guys follow that. So in example 1, we have edges 1 to 2, edges 1 to 3, and then finally edge 2 to 3, where if we were to add this edge, we would no longer have a graph that is a tree because we have a cycle. Because remember, a tree is an undirected graph that is connected and has no cycles. So if we add this final edge 2 to 3, we would be creating a cycle. Therefore, the answer is 2, 3. The edge that should be removed. So we have a tree. Over here we have edge 1 to 2, 2 to 3, 3 to 4. Now if we were to add edge 1 to 4, 1 to 4, this would create a loop, or this would create a cycle in the graph, and it would no longer result in a tree. So for now, let's keep in mind that this edge 1 to 4 would create a cycle. Let's see if the next edge is the one that we should remove. 1 to 5, if we add this edge, it would not lead to a cycle. Therefore, the only edge that should be removed is 1 to 4. So let's get to the drawing because I do want to point something out. Perfect. All right, so we have 1, 1 goes to 2, 1 also goes to 3, and then 2 goes to 3. So keep in mind that for this graph, we can remove any of these edges. If we were to remove this edge right here, we would get 1 goes to 3, and then 3 and 2 are connected. And this is a tree. So this is a valid tree graph. Now we can also remove this edge, and we have something 1 goes to 2, 2 goes to 3. And this is also a tree. So this is a valid tree graph, which was obtained by removing this edge right here. Now finally, we can also remove this edge, and we will be left with 1 goes to 3, then 1 goes to 2. This is also a tree graph, which was obtained by removing this edge. So no matter what edge we pick, no matter what edge we pick to remove, it could be this one or this one or this one, we would obtain a tree graph. But why is the answer specifically edge 2 to 3? Well, the answer is because, well, that's the answer because that was the last edge in our input. The insertion of this specific edge led to a cycle in our graph. Now, that right there is a really important sentence. Inserting this edge in our graph would lead to a cycle. So, how do we know whether it would lead to a cycle? If, let's say, let's keep in mind this edge 2, 3. Now, right before adding it to our graph, let's see if from starting at node 2, we can reach 3. If starting at node 2 we could reach 3, then we know this extra edge is unnecessary and would lead to a cycle. So let's test it. I'm starting off at 2. From 2 I can go to 1. Then from 1 I can go to 3. And 3 in this case is, well, 3 in this case is my target. Therefore, from 2 I could get to 3. Which means if I were to insert this edge, it would lead to a direct cycle. It would lead to having a cycle in the graph. Because this edge is completely unnecessary since I can already directly or indirectly reach 3. Now, one more time, just to stress this, since I can already reach 3 without the insertion of this edge, that means if I were to insert it, I can go back to 2, then I can go back to 3, and then back to 2, back to 3, like that. AKA, this means there's a cycle. So that's all we really have to test. For every single edge we are about to add, check if we can, starting at this node, the leftmost node of the edge, can we reach the other node? If we can, then we know this edge would lead to a cycle. And since, as the problem stated, if there are multiple answers, return the answer that occurs last in the input. Every time we are considering an edge and we're testing if we can reach the second node starting at the first, if we can reach it, let's update a variable. Let's not instantly return it. Let's instead update it in case we see another edge that leads to a cycle later on. And that's all that's needed to solve this problem. So now let's get into the code and write it out. First, I'm going to be creating my DFS function, which would tell me if I can reach one node starting from another. So let's say I'm starting at U, and I want to reach this node that I'm calling target. Let's first start off by creating a answer variable, which is an empty array. Let's also set n equal to the length of edges so we know how many nodes we're dealing with. Now let's create our matrix, where, you know what, let's call it adjacency list. I have a tendency to call it matrix even though it's more of an adjacency list. which is going to be an empty array for every number in the range of 1, sorry, in the range of 0 to n plus 1. Now keep in mind that I am going to be including a 0 in this adjacency list, and the 0 never gets used because all the vertices are labeled from 1 to n. And that's perfectly fine. That shouldn't be too much of a problem. Now for every pair, or for every edge in edges, let's create a visited set that's initially empty. And let's call a DFS function that will tell us if we start at node U, can we reach node V? So let's put out this function. U is our starting node, and then target is the node we want to reach. If U is in our visited set, let's just return false. And if U is equal to target, let's return true. The reason why we have this statement right here is because remember, this is an undirected graph. So we don't want to do too many recursive calls. So this is really a base case, just like this one right here. Now, if we haven't seen it before, let's add it to a visited set. And for every adjacent neighbor in this for this node, if the DFS starting at this new node V and trying to reach target, if this is true, let's return true. Else, and after this for loop, or after we try all the adjacent nodes for this current node U, and none of them return true, let's just return false. So now we can come back to this DFS where we initially call it, and if this DFS returns true, we know that the edge we're about to add would lead to a cycle in our graph. Therefore, let's set answer equal to UV. And let's add it. Let's go ahead and add it to our matrix. Oh, it's not calling this matrix, it's actually adjacency list. There we go. And then after all that is done, we can just return answer. So let's run through this code and make sure we fully understand it. N is just going to be equal to the length of edges, which tells us how many nodes are in our graph. Then we're creating this data structure that helps represent our graph. In this case, I'm using an adjacency list. Now for every edge inside our edges array, let's first initialize an empty set that would represent the nodes we've seen before. And let's call DFS starting at node U and with a target of node V. If we call DFS, which is this function right here, we want to return true if we can reach node V starting at node U. This true tells us that there's a path from U to V. And if our DFS returns true, that tells us that the edge we're about to add would lead to a cycle. So let's update our answer variable to be equal to this edge that would lead to a cycle. And then finally, let's append this edge to our adjacency list for both nodes U and V. And let's continue going through our edges array in case there's another edge that is a cycle. Because as the problem said, if there are multiple answers, return the answer that occurs last in the input. And this is not really that there is multiple edges that we have to remove. There's only one edge that we have to remove, but there's multiple possible edges that we could remove that would lead to a tree in this graph. So now let's run the code. Let's see if I made any mistakes anywhere. Okay, I didn't. Let's run some more test cases. And now let's submit. And it works perfect. So hopefully this video was able to help you guys understand how to solve this problem. If you guys appreciated it, then please leave a like and subscribe. Other than that, thank you guys for watching.